Welcome to Railway Track and Structures webinar entitled Mechanical Stabilization for Improved Trackbed Performance, which is sponsored by Tensar International. My name is Misha Wanek-Libman. I'm editor of RTNS, and I will serve as moderator for what should be an interesting look at trackbed design, construction, and maintenance practices. Increasing rail traffic is a mixed blessing. On one hand, more traffic means more revenue, but on the other hand, it also means increased stress on a railroad's infrastructure. Trackbed provides the literal foundation of a railway, and its condition can see positive or negative effects on other aspects of operations, including allowable operating speeds and safety. Practices that can reduce maintenance cycles and save on initial construction costs will help railroads do the one thing they really want to: run trains. As you will hear in a moment, the mechanical stabilization of ballast and sub-ballast using Geogrid provides a stiffer, longer-lasting structure with reduced deflection under load that can translate into improved trackbed performance. Our webinar will present design methodology and supporting information for the successful use of triaxial Geogrid for mechanical stabilization of the trackbed. Our speaker today is Brian C.G., who serves as Product Manager, Western Hemisphere at Tensar International. G directs the product management and analytics functions at Tensar and focuses on technologies related to ground stabilization and the optimization of transportation infrastructure. G has been with Tensar since 2006 and has been a licensed professional engineer with 30 years of experience. Before we hear from Brian, there are a few things which will help you get the most out of this webcast. First, you can adjust the speaker volume in the audio window on the display. Additionally, delegates can pose questions at any time during the presentation. Simply type your question in the Ask a Question space below the presentation window. I will put your questions to our speaker after he has completed the presentation. So without further ado, I will now hand it over to Brian G. for his presentation on mechanical stabilization to improve the performance of the trackbed.
Thank you, Misha, and thanks to everybody for joining today. Today I'd like to talk about several aspects of mechanical stabilization. First of all, the benefits of mechanically stabilizing track structures on operations and the structures themselves, how granular materials are stabilized using Geogrid, and then we'll move into design methodology in two applications. First, the stabilization of soft subgrades, and then the optimization of ballast and sub-ballast structures when the subgrade is already competent. Finally, we'll discuss some practical design and construction considerations and then go through some design and project examples. And finally, we'll have a question and answer session. Maintaining safe, efficient, and reliable operations in railway structures is increasingly difficult. As most of you know, I'm sure, freight volumes, loadings, material costs, labor costs, and most importantly, scrutiny are going up as more and more freight is moved by rail. At the same time, available maintenance windows and sources of quality aggregate are going down. This leaves us in a position where it's more and more difficult to maintain top-notch trackbed infrastructure. Improving the performance of the trackbed can offer big benefits, and innovative design approaches, materials, and construction techniques can be critical to improving this infrastructure. I'll start by talking about the benefits of mechanical stabilization as one means of improving trackbed infrastructure. Why should we look at mechanical ballast stabilization? The purpose of mechanically stabilizing ballast and sub-ballast is to create a more robust trackbed structure with higher initial stiffness and, more importantly, longer stiffness retention. Increased stiffness results in a decrease in the deflection of the track, both in a dynamic situation under load and also the permanent or plastic deformation that is known as settlement of the trackbed over time. Reduced deflection of trackbed has numerous benefits. First of all, longer intervals for surfacing and reballasting due to reduced breakdown of ballast stone and also reduced pumping of subgrade fines into the ballast stone. Ballast life extension can be 3 to 5 times that of unbound ballast layers. Less frequent maintenance events keep roads in service. We all know the cost of maintenance is not only the cost of the operation itself, but the lost revenue due to the downtime to maintain the track. Improved fuel efficiency. Some studies have looked at various means of increasing the stiffness of track bed and have shown that fuel consumption can be reduced up to 7%. A stiffer track bed yields a reduced risk of derailment due to less deflection under load and also less settlement that creates an uneven rail surface. And finally, less movement of the track bed results in less wear and tear on components such as rails, ties, fasteners, and insulated joints. Now let's talk about how Geogrid stabilizes aggregate layers, specifically track ballast. Mechanical stabilization consists of the interlocking of the ballast stone with the geogrid such that the particles of the ballast are confined at the base of the ballast layer. As more stone is placed and compacted on that layer, this confinement continues through the stone, resulting in a stiffer ballast layer with less particle movement. When the particles move less, then they abrade less, and also when they move less, the structure itself is stiffer. There's been numerous research studies around the world on the mechanical stabilization of ballast. If we look at just a couple of the outputs here, we can demonstrate graphically what the benefit is. This graph shows a study that was done at full scale, but in a laboratory setting, that compared an unstabilized structure with a stabilized structure over a soft substructure. And you can see a significant reduction in the deflection under load. Similarly, this graph shows the results from an in-field study where the track itself was instrumented to monitor settlement. And you can see the reduction in deflection after the installation of Geogrid under load. Both of these were dynamic deflection under load. If we then look at plastic deflection or settlement, you can see there's a similar benefit from Geogrid. This is another study on an actual rail line where Geogrid was installed on a line that had issues with settlement. There was a dramatic reduction in the rate of settlement of the rail line after the installation of the Geogrid. So you can see that this would result in a much longer maintenance cycle. One of the more interesting ways to look at the benefits of Geogrid in stabilizing ballast was conducted recently at Penn State University. This graph shows the results of a test that used instrumented particles of ballast with accelerometers to measure both rotational and directional acceleration, both with and without Geogrid. On the left, you see the movement of the ballast stones in all three directions with load without Geogrid in the section. And on the right, you can see the dramatic difference in movement of the ballast stone under load when Geogrid is installed. These graphs from the same study show the contrast between Geogrid and no Geogrid in terms of rotation. So here we're looking at angular acceleration. It shows that the particles rotate significantly less. And this slide shows a characterization of the rotation of a particular ballast particle, both in an unstabilized and a stabilized condition. You can see across the top, the unstabilized stone moves quite a bit under load, whereas the stabilized stone moves very little as the load is applied over time. So when we decide to use Geogrid for ballast stabilization, how do we apply it? There are two primary applications. First, at the bottom of the sub-ballast, in cases where we have poor subgrade conditions to improve the bearing capacity of the subgrade. And then within the ballast layer, to stiffen the ballast layer and extend the maintenance cycle and the performance of the track. Now let's look at the design methodology for ballast and subballast. When designing a trackbed structure in the United States, we use the Talbot equation to determine the thickness of the trackbed structure, H. The thickness of the trackbed structure is a function of the pressure at the bottom of the cross tie resulting from the load on the track and the allowable stress at the top of the subgrade, which is based on the ballast structure and also the conditions of the subgrade. The applied pressure is calculated as 2W times 1 plus IF times DF over A, where IF is the influence factor, which is a function of the velocity and diameter of the rail wheel, and DF is the distribution factor, which is a function of the type of tie, the tie spacing, and similar factors. W is the wheel load. The allowable bearing pressure, P sub C, is a function of the ultimate bearing pressure capacity of the subgrade in PSI and a factor of safety, which is set by ARIMA generally between 2 to 5. That depends on the railroad. So let's look and see how this design approach is used in the two applications, soft subgrades and track ballast optimization. For the stabilization of soft subgrades, we look at the P sub C, or the allowable bearing pressure, and we calculate that using the undrained shear strength of the subgrade and a bearing capacity factor that is determined based on whether we have geogrid or no stabilization geosynthetic in the system. You can see here typical values for an unstabilized N sub C and a stabilized N sub C. This bearing capacity factor, which is based on research by the Corps of Engineers, allows us to calculate the effective ultimate bearing pressure of the subgrade when geogrid is being used. This, combined with the factor of safety, gives us the allowable bearing pressure in both the unstabilized and the stabilized condition. This slide shows typical output for a design that was conducted in this way, and you can see the significant savings in the depth of subballast required here. In this case, we had a subgrade undrained shear strength of 6.1 psi and a factor of safety of 2.5, and we saved nearly 15 inches of subballast material. Now let's look at the use of geogrid to optimize ballast and subballast structures. In the case of track ballast optimization, we're dealing with a case where the subgrade conditions are good, or if we had poor subgrade conditions, they've been addressed. Now the designer can use the structural improvement from mechanical stabilization to optimize the track bed structure for the design conditions of the individual project. It's important to note that the design criteria vary by owner, by location, by the expected loading, and by other factors. But the idea here in track ballast optimization is that the designer can evaluate changes in the design configuration based on their effects on specific performance criteria in the track bed. These might include rail bending stress, tie bending stress, deflection of the track, or applied stress at the ballast surface. Here are some examples of the calculations that we might use in designing a track structure. So you see the calculation here for rail moment, deflection, or rail seat load. Each of these, which may be the design criteria depending on who the owner of the track is, incorporate the variable track modulus, which is designated U here. The effect of Geogrid in stabilizing the track structure is to increase the trackbed modulus. Track modulus is calculated in one of two ways. The rail is assumed to be a beam on an elastic foundation, and that track modulus is calculated as either the ratio of the wheel load per unit length over a unit of track deflection, or it can be calculated as the wheel load required to deflect the track 1 inch on one tie divided by the tie spacing. And it's important to note that track modulus can vary based on several factors. First of all, track modulus is higher during excessively dry periods when the subgrade soils are firmer, and lower when the subgrade is at or near saturation. Many railroads account for this by using different track modulus values by season. The type of track structure, including the rail type and tie type, also affects the track modulus. When mechanically stabilizing track ballast, you typically yield a trackbed modulus that is approximately twice that of an equivalent unstabilized section. This is based on empirical research. Tensar can provide guidance to you on appropriate values for different design conditions. If we're looking at track deflection and allowable track deflection, this chart from the Unified Facilities Criteria gives some examples of the allowable deflection in different conditions. You can see that as track wears and as ballast becomes fouled or deteriorates, the deflection would increase until we reach a point where the ballast needs to be either fully rehabilitated or at least resurfaced. This slide shows typical output from Tensar's design software for track ballast optimization in one particular case. What you see here is the ability to evaluate unstabilized versus Geogrid stabilized track for several different design criteria. In this case, with an allowable deflection of 0.25 inches, you can see that in number 7, the unstabilized track would have failed the design criterion. Likewise, if we had a specific subgrade allowable stress, in this case, we might have failed that as shown in number 6. Similarly, and graphically, we can show the deflection. Here, if we had a 0.25 inch allowable deflection, the stabilized condition might have passed while the unstabilized condition did not result in an acceptable design. The alternative for the unstabilized condition would be to use more thickness in the ballast to reduce the deflection further. This illustrates the difference between a stabilized design and an unstabilized design. Now let's look at some practical design and construction considerations. First, it is essential to consider variability in both the ballast stone and the subgrade properties. Subgrade conditions can vary widely across a project, and it's important that the designer have a comprehensive understanding of the subgrade conditions so that the design can be suitably conservative. Likewise, the strength of the ballast stone can vary quite a bit, and it's important to understand where you might be limited in terms of the quality of the ballast stone. There are also established design practices for many railroads that have to be incorporated. Many roads have minimum thicknesses, they have certain track modulus values depending on configuration, and in some cases they use fractions of the tie dimensions for analysis instead of the full cross-sectional area of the tie. These are just examples, but any of these established design practices need to be followed, whether designing in an unstabilized or a stabilized track bed. Another consideration is the depth of tamper head penetration in surfacing operations. In order to maintain the benefit of the geogrid, it's important that the tamper heads not impact the geogrid when the road is resurfaced. This typically is in the range of 10 to 12 inches in depth. So normally a geogrid design that includes geogrid in the ballast must have at least enough thickness to allow the tamper head to go above the geogrid during surfacing operations. When it comes to reballasting, it's also important to note that there is some limitation to the compatibility of using geogrid with standard automated reballasting equipment in North America. The clearance beneath the track using conventional automated reballasting equipment can make it difficult to get the geogrid into place during a reballasting operation. What this typically means is that the geogrid is normally deployed in areas where there are significant issues that justify its use, or in new construction where the reballasting operation is not a problem. Also, when constructing over fine-grained subgrades, a well-graded sub-ballast layer or possibly a non-woven geotextile may be required to maintain separation of the fine-grained subgrade soil from the ballast itself. And finally, it's important to consider size compatibility between the stone and the geogrid. A typical ratio is the D50 of the stone should be less than or equal to the aperture size, which should be less than or equal to twice the D85 of the ballast stone. Tensar offers design software to allow these analyses to be performed easily. Our SpectraRail software allows the user to perform design analysis for sub-ballast layers over soft subgrades, both with and without geogrid for mechanical stabilization, and also to evaluate and compare designs for both unstabilized and mechanically stabilized railroad beds with comprehensive cost analysis for all alternatives. You can also estimate the track settlement for a specific level of performance or a specific loading. Now let's look at a couple of examples of applying mechanical stabilization to rail bed design. The first example relates to mitigating maintenance issues related to poor subgrade. In this case, we were dealing with a 1.25 mile long section of freight rail in the southeast United States. There was excessive settlement and pumping of subgrade soil due to poor subgrade conditions. These conditions included a high water table, poor drainage, and very fine-grained clay soil. Maintenance and surfacing at one point was being required every 2 to 4 weeks, and despite that intensive maintenance, a speed restriction of 5 miles an hour was placed on this section of track. The alternatives that were being evaluated included full relocation of the track, but also mechanical stabilization of this section using geogrid. Here are a couple of photographs of what the track looked like when it was having difficulty. You can see on the left, it's obvious the fine-grained clay soil has pumped up through the ballast, weakening the ballast. And on the right-hand side, you can also see the areas where the fine-grained soils are pumping up, and if you look carefully, you can see even some deflection in the rails that were the cause of the speed limitation. In this case, the chosen solution was to stabilize this section of track with geogrid. First, a non-woven geotextile was installed for separation of the fine subgrade soils from the overlying ballast. Then the ballast was stabilized using geogrid with a minimum depth of 12 inches below the ties to accommodate tamping operations. After 3 months of operation and no maintenance issues, no track stability issues, the railroad raised the speed limit to 35 miles an hour from 5. And shortly after that, all speed restrictions were lifted. Maintenance intervals also were restored to normal. Our second example is a rail spur at a major port where the spur was being installed, and we looked at mechanical stabilization to optimize the structure and minimize the cost. The parameters for the design are listed here: a 40,000-pound wheel load. You can see the wheel diameter. Maximum speed was relatively low at 10 miles an hour. We were using timber ties spaced at 20 inches on center, and we were building on a 2% CBR. The target factor of safety in this case was 2.5. So just running through the Talbot equation to determine the various values so we can illustrate here. The influence factor in this case was 0.09. You can see the calculation here from the maximum velocity and also the wheel diameter. The distribution factor, using the chart from the ARIMA manual, was 40%. As you can see here, 0.40 for the DF, which corresponds to the wood ties that were used in this case. Therefore, the applied pressure at the top of the ballast was 38 psi as calculated here using the Talbot equations. Now we needed to determine the allowable bearing pressure. And using the formulas that I showed you earlier, you can see we calculated both an unstabilized allowable bearing pressure and a stabilized allowable bearing pressure. 9.7 psi in an unstabilized case and 20.2 psi in a stabilized case. If we use the values we've calculated and go back to the Talbot equation, you can see that the required total thickness of ballast and subballast in an unstabilized case is 29 inches, while in a stabilized case, it's 16 inches. So looking at the original design, we came up with several options for the stabilized section. In the case of the unstabilized section on the right, we had a 12-inch ballast layer over a 17-inch subballast layer. With a stabilized roadbed needing only 16 inches of total thickness, we had 3 different options. The first option shows a 12-inch ballast layer over 6 inches of subballast. This totals 18 inches, not 16, the reason being that there is a minimum thickness to be placed on the geogrid of 6 inches in order to achieve full interlock. The second option is a 9-inch ballast layer, which was the minimum allowable, over a 7-inch subballast layer. This gets us to the 16 inches of stabilized roadbed. And then the third option was to use the minimum 9-inch ballast layer, but to slightly increase the subballast layer to 9 inches as well. So the total thickness here is 18 inches, and there is an additional factor of safety. In this case, the third option was used. And if we look at the savings associated with the use, with these costs for materials, $30 per ton for the ballast aggregate, excavation and disposal of subgrade was $20 per ton, and the geogrid was $4 per square yard. If you look at the cost savings per square yard of roadbed structure, we saved $25 per square yard. And for this 11-mile long rail spur, the savings to the port was $2.2 million for an equivalent structure. There were some other advantages to this design as well. Ports are usually very congested areas. We significantly reduced construction traffic by 728 fewer trucks bringing stone in and 728 fewer fill trucks taking excavated fill out. We accelerated the construction schedule. There were 1,456 fewer truck hours required, so the structure could be built more quickly. Also, in many ports, there is concern about the potential excavation of contaminated soils. By reducing the amount of excavation, we reduce the risk of excavating and having to dispose of contaminated soils. There were reduced carbon emissions, primarily associated with the reduced number of trucks required for fill. The typical reduction in carbon emissions is 20 to 40% with an fully optimized ballast structure. And we also enhanced the long-term performance of the roadbed structure because by building 9/9, we actually added a little bit of thickness beyond what would have been required for an absolutely equivalent structure. So let's look at a summary of what we've discussed today, and then we'll move to question and answer. First of all, mechanical stabilization of ballast and sub-ballast offers a tremendous opportunity to build and maintain more robust track bed structures with reduced dynamic deflection and settlement. These improvements can provide reduced construction costs, longer maintenance intervals, reduced operating costs, longer component life, and safer operations. The benefits of mechanical stabilization using Geogrid can be incorporated into standard design methodologies through the use of bearing capacity factors and trackbed modulus values. Tensar offers Spectra Rail software that allows the designer to develop optimized solutions incorporating mechanical stabilization, in addition to the ability to do conventional designs without Geogrid as a comparison. It's very important, though, to understand the design, construction, and operational aspects of mechanical ballast stabilization in order to maximize the benefits of using the Geogrid. I thank you very much for your time today, and I invite any questions at this point. Thank you.
Thank you, Brian, for that thought-provoking presentation. We have a lot of Q&A, which is great to see, so we'll just jump right in here with our first question. Is there a minimum or maximum depth of stone to be used with the Geogrid?
Yes. As far as a minimum depth, Tensar recommends a depth of no less than 6 inches of stone ever on the Geogrid, just to give enough stone to create full interlock and get the benefit of the grid. When we talk about a maximum depth, the discussion changes. It's really a matter of how far does the confinement effect extend up into the stone above the grid. We have research with various different kinds of stone that indicates that the confinement effect extends upward approximately 1.5 to 2 feet from where the Geogrid is in the section. So there's not really a maximum depth, but it's important to understand that the confinement effect doesn't go on forever. If you have a very, very thick section, when you get above an 18-inch thickness, if you're counting on full confinement, you would want to use a second layer of Geogrid to continue the confinement effect upward.
Okay, and moving on to the next one, where do the bearing capacity factors for subgrade stabilization come from?
The factors that I showed in the example here come from the Army Corps of Engineers research on unpaved roads in various different loading conditions. We found that they translate well to this application as well. They're theoretically based in some cases, although in the case of the Corps of Engineers, they were completely empirically derived. I think it's important. I saw one question further down the queue, I believe, that talked about the origin of the bearing capacity factors and why we were using specifically 2.8 in the unstabilized case. There are some different uses of bearing capacity factors in embankment design. In this case, the research on wheel load type structures indicates that the factors I've used here are in the range of what you want to use. I would also point out, though, that we have research that shows that the bearing capacity factor in a stabilized case with Geogrid does vary depending on what type of Geogrid is being used. So it's important to tie some empirical testing to the specific product that you intend to use so that you can make sure you've got an accurate bearing capacity factor.
Sounds good. And how do you determine whether or not to use a geotextile with the Geogrid? Second part of the question, what kind of fabric?
The decision with the Geogrid to use a geotextile is a function of maintaining separation if you have fine-grained subgrade soils. So we talked a little bit in the presentation about degradation of the ballast creating fines, but certainly in the example, the first example I showed, you could see that the pumping of fines there was not fines from the ballast, but it was the underlying fine-grained clay that was pumping up into the ballast and weakening it. With Geogrid, it's possible to create a separation layer if you use a well-graded stone layer in order that creates a natural filter. However, depending on your design, you may not have room or you may not have the ability to use a well-graded stone layer to create that filter. And in that case, you would want to use a non-woven geotextile to maintain separation between the fine-grained soils and the ballast or the sub-ballast. The calculation to determine that filtration ratio is known as the piping ratio. It's a straight calculation that's used in all kinds of filtration. There's some information on it on Tensar's website, or you can certainly call your Tensar representative for some assistance with the calculation. But it's not specific to Geogrid, but it's a matter of maintaining filter at the confinement interface.
Okay, and next one's a question about software. How can they access? How can I get access to Tensar's design software?
We offer the design software to the rail community free of charge. However, we offer it on a case-by-case basis. It's a little more complicated than some of our other software, and there's more underlying design expertise needed to properly use it than with some of our other software. So you can either contact your local Tensar representative, or you can send an inquiry to web@tensarcorp.com, web@tensarcorp.com, and someone will contact you about getting you the software.
Okay, and how is the improvement in track modulus with Geogrid determined?
We determined the improvement in track modulus based on empirical testing, comparing unstabilized sections with stabilized sections. And we do this with a variety of thicknesses and also with different geosynthetics. So the values that we're using are based on our testing. Certainly this is the only way that we know of right now to quantify the benefit. We try to make sure that the benefit that we put forward is conservative, but it's based on empirical testing.
Okay, and are Geogrids approved by ARIMA?
I'm sure everybody on the call knows that ARIMA is the American Railway Engineering and Maintenance of Way Association, but I'll spell that out just in case. ARIMA actually does not approve any products. So it's important to know that while Geogrids are included in the ARIMA manual, that doesn't constitute an endorsement by ARIMA. It simply is technical guidance. That said, it's important to understand Geogrid is included in the ARIMA manual. Currently, there's a table that includes two of the prior generation Geogrids, and properties for those materials are called out in the manual. When you look at newer geogrids, for instance, our Tri-X geogrid was introduced after this table was created in the manual. There's a provision in the AREMA manual that allows the use of any new product that's not covered specifically in the manual. It requires or it recommends, I'm sorry, that the material be submitted to the engineer of record 15 days prior to bid date. It requires the existence of full-scale laboratory and in-ground testing of the material. It also requires comparable projects that can be cited to show some experience with the material, and it requires the submittal of, or recommends the submittal of a sample with certified spec sheets. So there is a way, and just by way of example, Tensar's Tri-X geogrid can meet these criteria, and that's how we use it on rail projects. But so AREMA does have recommendations around these materials, and they can be found in the manual.
Okay. And can you talk a little bit about how drainage is improved through ballast stabilization, or if it is improved through ballast stabilization?
Yeah, when we talk about drainage and ballast stabilization, it's more a function of maintaining the drainage than improving it. The geogrid itself does not do anything to improve the drainage by virtue of being in the section. But what it does is it preserves the ability of the section to drain properly over the long term. The things that inhibit drainage in a rail section are those fines that we talked about before, the degradation of the ballast, the pumping of subgrade fines that clogs the ballast and doesn't allow water to get out. So the stabilization using geogrid, what you're accomplishing there is the preservation of drainage, not so much as more than the improvement. Okay.
The tests that you referenced in your presentation, were they with limestone ballast? What about granite ballast that doesn't degrade and generate fines as easily?
Yeah, the testing was with limestone ballast, to my knowledge. I think the best way to answer this is clearly better quality ballast stone is always going to be favorable, but the confinement effect of the geogrid is the same no matter what stone you're putting in there. So by reducing the movement of the stone and the ability or the capacity of the stone to abrade itself, you're going to gain a comparable benefit. Now, granite ballast is going to last longer than limestone ballast no matter what, but the benefit of the geogrid in terms of stiffening the section and reducing movement is going to be the same. I think it's important to note that the confinement effect and the stiffening that results from confinement of the stone is distinct from the benefit that comes from reducing movement and degradation of the stone, because bound stone is stiffer than unbound stone. So you're going to get benefit there as well as from the reduction in movement.
Okay. And do you have any idea if geogrids have been applied to stabilize differential settlements associated with permafrost degradation?
We have seen geogrid used in rail applications in cold climates. It's a very difficult thing to quantify what the benefit would be, but a stiffer structure over permafrost or in a frost heave situation should provide a benefit. Certainly, if the structure is stiffer and resist deflection from load from above, it's going to also resist deflection from load from below. But I don't know of any study to quantify that at this time.
All right, and the next question kind of tags on to the previous question here. Would geogrid have any benefit reducing movement from freeze-thaw cycles?
Yeah, I think it's a very similar answer. We do believe and we've seen benefit there, but it's not something that is easy to quantify. Certainly, you could look at other ways to mitigate freeze thaw, in particular, in terms of some kind of capillary break layer or something to keep the freeze thaw below the track section itself. But there would be some benefit from the stabilized section.
Okay. Have there been any studies done for passenger or commuter lines? Let's see. I'm assuming this is, has there been any studies on how a geogrid can be applied on passenger and commuter lines? I think that's what this question is. Yes, my apologies.
No, it's all right. I'm trying to make sure that I answer the question that's being asked. As far as studies, we tend to focus probably towards the heavier loadings because it's a more intense situation. You try to study in the worst case. That said, there are a number of installations of Geogrid in passenger and commuter lines, both in the United States and around the world. Specific ones that pop to mind are in Dallas and also in Utah. I'm sure there are others. That's the two that occur to me. Also, stabilization is used widely in Europe, and most of the lines there are passenger lines. So, yeah, it's widely used for that as well as freight.
Okay. And does the Railbed design software offer analysis of multiple layers of Geogrid in ballast/sub-ballast?
It does. You can analyze both a ballast and a sub-ballast stabilization layer. And certainly beyond that, if you have any, I assume if you're asking the question, you either have the software or you're going to request it. Certainly, whoever helps you get the software would be also happy to support you and help you deal with the specific application you're talking about.
Okay. Have industrial track owners been applying this solution to their track, whether new installation or rehab?
Yeah, actually, I have some personal experience with this one. Earlier in my career at Tensar, I was called to a site where it was an industrial rail spur coming off of a Class 1 line, and the subgrade conditions were so soft that when they were trying to clear the area for the rail spur, they had sunk the track hoe up to the cab. The engineer on site sent me a photo over on his phone saying, "Help, I need some assistance here." And we ended up devising a solution, and it was a two-layer solution to create the embankment there. So it was effectively a sub-ballast stabilization layer to create the embankment for that spur. We monitored the settlement of the spur for about 6 months with the consulting geotechnical engineer to make sure that we had consolidated all of the soft organics that were underneath it, and then they built the spur on top of that once we had it settled and in place. It was a very successful project.
Okay. Was the project where you reduced aggregate thickness with grid on an industrial track, or was it mainline?
That was on a spur into a port. So I'm not sure how you'd classify that. I guess it's not, I don't know if that counts as mainline or not. I believe the spur was owned by the port, not by the railroad, so I guess in that sense it's not mainline, but it was one spur into the port.
Okay. Is Geogrid in mat or roll form, and how do you connect Geogrids throughout the work limits?
The Geogrid is normally furnished as a roll. It's typically either 50 or 75 meters in length, although there's various different lengths available, and that really is immaterial. As far as how you connect it, the roll to roll, the only thing needed is overlap. It's typically 1 to 3 feet of overlap, and the reason for that is that the stone that's being placed on the geogrid actually ends up striking through both layers, and once you have that interlock, there's no need to connect it. Sometimes over very, very soft soil conditions, it may make sense to use zip ties or something like that to hold the pieces of geogrid together, but the only reason for that is for constructability. It's not needed for the function of the geogrid.
Okay, and is it better to have the geogrid between the subgrade and subballast, or between the layers/lifts of subballast?
Typically, the best place in a subballast stabilization application, the best place to put the geogrid is directly on the subgrade. And the reason for that is that whatever subballast material might have been placed below the geogrid in a soft soil situation is going to end up sacrificing under load down into the subgrade. So the effective thickness is reduced as that happens. The geogrid, while it's not the primary function, one of the things that the geogrid does is it keeps the subballast materials above the grid. It doesn't allow the stone over time to work down into the soft subgrade where it's not doing any good to the design. So in a soft situation, we recommend rolling out the geogrid directly on the subgrade if that's possible. If it's very, very soft, as in the case of that rail spur I described a minute ago, you would actually probably want to leave as much of the vegetation in place as you could, root mat type stuff, just to give the geogrid something to ride on until you get an initial lift on it. You don't need to grub it out completely. Obviously, you want to cut out big trees and stumps and things like that. Now, it is, by the same token, should be understood that the confinement effect of the geogrid does go in both directions. So if the geogrid's up in the section, as an example, if it's in a multi-layer system, then the confinement by locking it in place works both ways. But when you're talking about below subballast, which usually means you're on some kind of soft soil, I would lay it right on the subgrade.
Okay, and how would the stabilization change with concrete ties? Or does it?
Yeah, it's effectively the same. I mean, the inputs to the equation, to the Talbot equation that concern the type of tie don't really have anything to do with the geogrid itself. You know, they have to do with the distribution factor that goes into the equation. So really, no matter what your tie type is, that's just accommodated elsewhere in the design.
Okay. Is there any type of reference that can approximately give a table of factors for improving the strength of subgrade or subballast?
Sorry, I'm just trying to, I'm going to go ahead and read that just because I didn't,
okay.
I'm afraid I didn't get the question exactly right.
Okay.
Strength of subgrade or subballast. There really isn't a table like that. You know, we do the calculation within the Talbot equation for the effective or the allowable bearing strength, and that's, or bearing stress, I'm sorry, and that's really the way we quantify that. So you will be able to, there's an assumption there that you have a fully confined layer with the geogrid, and that results in the bearing capacity improvement. But I don't know of any table that lays that out and says, you know, depending on different factors, what the improvement is.
Okay. For the, whoops, sorry. Can you address the effect of geogrid on ballast draining and mud pumping?
Yeah, I mean, this is it's sort of a different discussion of the earlier question. As far as ballast drainage, what you have is preservation of drainage. If the ballast drains well, then having the geogrid there to maintain the quality of the ballast, prevent ballast breakdown, is going to maintain that drainage. The geogrid doesn't in and of itself do anything to improve the drainage. As far as mud pumping, that's similar to what we were talking about earlier with separating the fine-grained soil. So if you can have a sub-ballast layer in place where you can achieve filtration as measured by the piping ratio, then you can eliminate the pumping of those fine-grained soils from below. If not, then you're going to need the non-woven geotextile to create the separator or to act as the separator. I think it is important to note that when you're talking about separation, we do recommend a non-woven type geotextile. Wovens have been used in this application, and there's been some issues with them blinding with the fine-grained soils. Wovens have their own applications, but in this case, when we're talking about geogrid, we typically recommend a lightweight non-woven geotextile that would be placed below the geogrid. That's the other thing that's important. You would place the non-woven geotextile first and then the geogrid, because that's the only way to maintain confinement when you place the stone on top. Obviously, if the geotextile is on top of the geogrid, you won't get, the stone won't strike through the grid and interlock.
All right. And what is the design life of the Tensar material?
That's a good question. I mean, it's basically unlimited. Every other part of a trackbed structure is going to deteriorate before the geogrid because it's made out of polypropylene. It's stabilized with carbon black. If you put it in a landfill, it would last forever. It probably would just about last forever in a trackbed structure.
Okay. What is the minimum spacing in between the layers of geogrid? Would 4 inches be acceptable? The questioner would like to know.
Yeah, I mean, we would prefer to see 6 inches between the layers as a minimum, but I should point out that even 6 inches would really, I think would best be viewed as over-designing the structure. The confinement effect of the geogrid extends probably 18 to 24 inches above it. Now, that doesn't mean that you want to necessarily go all the way to 24 to maintain full stiffness, but to put the layers of grid that close together really would probably be just buying too much grid. And that's the Tensar guy saying that.
Okay. And this will be the last question here because we are coming up to the end of our time. Does the Tensar program calculate the price difference between triaxial and biaxial geogrid?
It does. It does it as a user input. So there is a cost module in the software that allows the user to analyze the cost of the different solutions they come up with. Part of that is the cost of the geogrid. So obviously the cost of geogrid depends on the location and the type that you've selected, and distance from where it's made and various other things, because you do have to ship it. So that's a user input.
Okay. Well, again, I thank you all for joining. Thank you, Brian, for a highly informative presentation, and thank you to Tensar for sponsoring this event. One quick note for those of you going to Railway Interchange, Tensar is exhibiting in booth 4808 in the REMSA section. There are a lot of questions we weren't able to get to due to time constraints today, but representatives will be there to answer any questions, I'm sure. And on one last final note, the webcast will be available on demand to listen to again. Delegates who have signed up will receive an email when this is ready. Thank you again for joining and for taking part in today's webinar.